Welcome everyone. Today, Professor Bimal Kumar Sinha is our honorable speaker. He is a very well-known figure to the global statistical community, and he is currently holding the position of Presidential Research Professor at Department of Mathematics and Statistics at University of Maryland, Baltimore County, USA. Professor Sinha has published numerous research articles in different areas of statistics, including multivariate analysis, ranked set sampling, statistical meta-analysis, environmental statistics, and many more. He has 4 authored volumes and several edited volumes to his credit. He supervised more than 30 PhD students. From his long list of awards and accomplishments, he is an elected member of International Statistical Institute. He is a fellow of Institute of Mathematical Statistics and a fellow of American Statistical Association. Today, he is going to talk about statistical meta-analysis, and the title of his talk is An Introduction to Statistical Meta-Analysis with an Application. With that, let us welcome Professor Sinha to deliver the talk. Over to you, sir.
Thank you. Thank you, Shomon, and thanks to everybody. I thank the head of the department, Bishajit, for the kind invitation. What happened during the pandemic, so during the last couple of years, I am reaching out to many Indian universities. So yours is number 20. So all over India, I got in touch with various stat departments or Department of Math and Stat, and I wanted to know the statisticians back home. So that was the basic idea. So by now, I got to know so many of you from all over the country, and of course, I also expressed an interest to give a seminar. So I do that quite regularly, almost every week. At some of the Indian universities, I do that. So it's very nice to be today part of your prestigious department and the university. Now, before it became PU, it was the Presidency College under Calcutta University, and your college produced so many brilliant statisticians from in the hundreds. And my all-time favorite, my hero, my big brother, Jayanta Kumar Ghosh, is a product of your department under the college, So he's my all-time favorite and all-time big brother, So I was very close to Professor Ghosh, and unfortunately, of course, a few years back, he passed away. And as you know, Dr. Ghosh was a former director of the Indian Statistical Institute and also a former president of the International Statistical Institute and a follower of C.R. Rao. Dr. Rao, who was born on September 10, 1920, is now 101 plus. And about a couple of years back, can you put the slide back, please? The C.R. Rao slide. Shubhan, what happened to the slide? Yeah, please keep it here. So on September 10, 2020, when Dr. Rao completed 100 years, so on behalf of the STAT group at UMBC, that's what you see here, the statistics group at UMBC, on behalf of all of us, we sent this the birth centenary congratulations to Dr. Rao. So, and about 5 years back, myself and my twin brother Vikas Sinha, he's a former faculty of ISI Calcutta. We visited Dr. Rao. Dr. Rao, of course, by now he's very old. He's now very old, and then he's now he lives with his daughter in the city of Buffalo. So we visited Dr. Rao for one afternoon. We spent about 4 or 5 hours with Dr. Rao, and here I have Dr. Kirti Shah from the University of Waterloo, a former student of C.R. Rao. So, we made it a point to visit Dr. Rao. He was then, I think, 95 or 96, but he was very alert, and we had a good time, for a few hours. So that was so I make it a point to to express our, of course, whatever you can say about C.R. Rao, and he's still alive. That's very nice. We are all blessed to be. And I was blessed to be a colleague of Dr. Rao for about 6 years at the University of Pittsburgh, 1979 to 1985, before I joined UMBC. Okay, all right. Next slide, please. What happened to the what happened to the book card or the title of the book? No, go up, please. Okay, go down, please. Next one. Yeah, there was a nice picture of the book. That picture is gone. Anyway, okay, all right. I think the second slide was the John Wiley publication of our book. There's a very nice picture. I don't see it now. Anyway, so I have divided my talk into 2 parts, part 1 and part 2. In the first part, I'll give you an overview of statistical meta-analysis, kind of storytelling idea here, absolutely completely non-technical, through some motivating examples to explain the basic idea about statistical meta-analysis. I'll give you about 6 or 7 real-life examples of statistical meta-analysis. That will be in part 1. And in part 2, I'll select one of the meta-analysis problems and we'll do a little bit of theory there. So second part will be a bit technical. I mean, naturally, we cannot avoid math or stat formulas altogether. So the second part will be a bit technical, but the first part is very, very general idea. Okay, so let's stay here. What is the meaning of meta-analysis? So you are all familiar with, like the Greek ideas, like alpha, beta, gamma, theta, delta, zeta, same idea. So meta. So meta-analysis means more analysis, like metadata. Metadata is more data. Lots of data, that's metadata. So meta-analysis means more analysis. Why? Why more analysis? Some analysis has been already done. As statisticians, we collect data, do some model building, do the data analysis. So some analysis has been already done, but we are not happy yet. We want to do more. That's the idea of meta-analysis. Why do you want to do more? They are called the primary studies. Some studies have been already worked out, but we cannot stop there. We need to do a little bit more analysis. That is the part, that's the second part. That's called the meta-analysis, more analysis. And that is the task of a meta-analyst. Like if I'm a meta-analyst, that's my job, is to look at the data analysis that has been already done, and I want to complete that process. That's meta, and do more analysis. So I'll be working as a meta-analyst. That's the idea, okay? So let's look at the first example. Good. The very first example, let's go back in time, 1953. Long time back. I was a baby then, I was about 6 years old. So this happened in 1953 at the University of Chicago. Paul Meyer, the Kaplan-Meier estimates, that Paul Meyer was a statistician. Of course, he was a very young man at that time at the University of Chicago. So sometime in spring in 1953, around this time, some of his chemist friends from the chemistry department, they came to Paul and they presented to Paul this data set. What they did, they conducted 4 experiments to get a sense of the percentage of albumin in plasma protein in human subjects. So that was the goal of their experiments. Percentage of albumin. You want to get a sense of the percentage, mean percentage, average percentage of albumin in plasma protein in human subjects. So that was the common purpose. And they conducted 4 experiments labeled here A, B, C, D. They are the sample size, they are the human subjects, human volunteers, 12, 15, 7, and whatever number I cannot see it, 16, yeah. And then you have the 12 measurements, 15, 7, and so on. These are the raw data summarized in the form of sample mean and sample variance. So that's what the chemist friends did. And then they wanted to know from Paul. So this is the data. How do we get a sense of the population mean percentage of albumin? If we look at the data, we have results from 4 experiments. They are independent experiments, all of them addressing the same goal, common goal. That's very important in meta-analysis. So all the 4 experiments have been done, conducted. Now, you see, there's a need to combine. There's need to combine the results of these 4 independent experiments. So these are called the primary studies. The experiments have been conducted already, and these are the results. But we are not done yet, because the central goal is to draw inference about the population parameter, which happens to be in this case the mean percentage. And we have the data here, we have the sample means and the sample variance and the sample size. If you look at the sample means 62, 60, 59, 61, in spite of the fact that the sample sizes are so small, 12, 15, 7, and 16, very small sample, but the sample means are so close, suggesting that yes, behind this is the sample, right? There's a population here, population of measurements generated by experiment A, B, C, and so on. So this sample, the mere closeness, they're so close, suggests that yes, the data in the experiment generated by experiment A, B, C, D, they all share a common population mean, which we can denote by mu, which is the common mean, because look at the sample base, they're so close. And of course, there's some variation in the experiments, like sigma square A, B, C, D. What about the unknown? What about the population variances? We cannot assume that, of course, they are unknown, and we cannot even assume that they are equal, because look at the sample variances, 13, 7, 33, and 16, 18. They're so different. So here the problem is we conducted 4 experiments, the sample means are very close, and the sample variances are very, very different, small sample size. So how do we combine the results of these 4 experiments to draw inference about the unknown population parameter, which happens to be in this case the mean percent, the population mean percentage of albumin. So there's a common population mean. How do you draw inference? The chemist friends knew that if I had only one experiment, the sample mean is a nice estimate of the population mean. We have the sample variance, we can estimate the population variance. So we can do a little bit of t-test, and we can use the t-statistic to have a confidence interval for mu. So that much they knew. But they had no idea how to combine the results of these 4. That is called meta-analysis. Combining information from independent, that's the definition of meta-analysis. Combining, so you have to develop a method how efficiently we can combine the information from independent experiments about a common parameters. See, all the 4 experiments, they provide information about the underlying population parameter, right? Now, so how do we combine the evidence? They are also struggling with the idea that the chemist friends, they are struggling with the idea that, and in fact, they suggested to Paul, will it be okay if we ignore the results of experiments A, C, and D and keep only results from experiment B, because that seems to be the most precise with the sampling variance, the least, only 7.8 compared to other variances. So their idea was that if Paul says it's okay to ignore the results from A, C, and D, then they'll be happy, because then there's only one population, they know how to deal with it. Sample mean, sample variance, they are familiar with the t-test and so on. Of course, Paul's immediate response was, no, once and that's the thing in statistics also, once we spend some money and time and resources to collect the data, so the data should not be wasted, and we must come up with a method to combine. Because after all, all these experiments, they do provide information about the underlying parameter, right? So how do we combine? That is the problem in statistical method. Same idea in example 2. Here the problem is to get a sense of mean selenium in non-fat milk powder. Again, there are 4 experiments. The sample sizes, they're small, and they look at the sample means. Not all that close, but we can assume that there's a common. After all, the sample means are sample sizes are very small. So you can assume that perhaps again also a common mean in the population, but the variances are very, very different. 86, 21, and 3 and 33. So the unknown population variances, they're very, very unequal. But there is a common mean, so there is a common mean. So the question here is, how do you draw inference about a common mean when you have samples from the population and the variances are unknown and unequal? So my second part of the talk will be exclusively, we'll deal with this problem. We'll address this problem in the second half. But in the first half, let us look at some more problems of statistical meta-analysis. I'm going to skip number 3. Let's go to example 4. Thank you. Yeah, let's keep it here. It's a very common problem in statistics. What do you want to do? We have 2 studies, the experimental study and the placebo or the control group, experimental group and the control group. What is the problem? The problem is we have a certain medicine, amlodipine. By the way, I take this medicine every day. So there's a medicine amlodipine for the treatment of, I don't know what is angina, but I have some other problem. Anyway, so we want to know whether this treatment is effective or not. That's fine. So we have 2 groups, the experimental group and the control group. This is a 2 sample problem. We do that all the time, even at the undergraduate level. And the response here is the continuous response. So based on a sample of size 46, we have 46 raw values. Then we compute sample mean, sample variance in the experimental group, likewise here. So one study is based on a sample of size 46 in one group, 48 in the other group, and the sample mean, sample variance, sample mean, sample. This is classical 2-sample problem. So we are interested in probably testing mu1 equal to mu2 or estimating mu1 minus mu2. That's what we say, standard problem. Sample size is large, 46, 48. So you can assume normal, very easy solution here. Except that we don't have 1 experiment, we have 8 studies for the same problem. Why there are so many studies? And we have the temporal spatial nature in these studies. This is a global problem. It's not your problem or my problem, India problem or US problem or Canada problem. It's, when it comes to human health, it's a global problem. So all the 8 studies have been carried over the globally and different time points, but all of them addressing the same issue, whether this medicine is effective or not. So we have results from 8 studies now. So naturally, you can say these are called the primary studies, these 8 studies. So the person or the agency, they're interested in combining the information, they will come to a meta-analyst like me or like you. They'll come to the meta-analyst, they'll present these results. Then we have the results of these 8 experiments. This is the problem. Statement of the problem is right here. We want to study the effectiveness. And there are 8 experiments, and this is the results we have. So how do we combine the information from these experiments? Naturally, some of these experiments might suggest that the treatment is effective, while others may not. So there could be a mixed signal. But anyway, how do we combine the results of all these 8 independent studies? So that finally, at the end of the day, we can say that yes, upon conducting the meta-analysis in an efficient way, here is the verdict. Yes, the treatment is effective or not. When you have the evidence, when you combine the evidence from so many studies, it will only strengthen your conclusion. That's the idea also. Like if there is just one study, you are not sure whether we are getting the correct thing or not. After all, then there's sampling variation. But when you have information from all these independent studies and you combine the information, that's the whole idea. So meta-analysis is the synthesis of information, combining evidence from independent studies. So the methods are called the meta-analysis methods. So I have we missed the slide. That was slide number 2. I have a book on meta-analysis published by John Wiley in 2008. So the book has about 15 chapters, all sorts of issues in statistical meta-analysis, all various methods of conducting statistical meta-analysis, depending on the scenario, of course, application will be different, and some parts can be very, very theoretical. So I have some papers on meta-analysis in JASA, and there are many papers on meta-analysis in the Annals of Statistics also. So, so it can be very theoretical. And likewise, there are many papers on statistical meta-analysis in many applied journals also. Okay, so it can be both theoretical and applied in nature. Next one, please. Nice problem for the treatment of non-ulcer dyspepsia. Here is a medicine, cisapride. So you want to know if it is effective or not. Same idea. So you have results of now 13 studies, but this time the response is yes, no type, success, failure. In example 4, you have the continuous response, but here the response is discrete type, yes, no, but only response. So again, very standard two-sample binomial problem, pi 1, pi 2. So you want to know whether pi 1 is equal to pi 2, or you want to estimate pi 1 minus pi 2 and do testing and all that. Except that now we have results from 13 trials or 13 studies, but the problem is the same. Again, why there are so many studies? Because it's a problem. Maybe we want to know whether this treatment is effective or not. There's a study in India, there's a study in the US, there's a study in Mexico, one study in Australia, one study in maybe New Zealand, like that, all over the globe. All these different studies at different time points. We are all trying to figure out whether this treatment is effective or not. So naturally there will be many studies, and so we have all these studies. And look at there's a common problem, independent studies, perfect scenario for meta-analysis. So meta-analysis will be how do you combine the evidence we have from all these 13 studies, all of them addressing the same problem. So what is the final conclusion? Is the treatment effective or not? So there's a standard pi 1, pi 2 problem. In the example 4, it was mu1, mu2, but here it is pi 1, pi 2 problem. Okay, so it is possible that we can test the quality of the pi i's, and but then we have to combine the information from all the 13 studies. Some studies may accept, some studies may reject. Or if I construct a confidence interval for pi 1 minus pi 2, then we have to make sure that we can combine efficiently the result from the 13 studies. So that's the whole idea of meta-analysis. We have to develop methods to efficiently combine the information from independent studies. Of course, the problem is the problem can be defined. Like here, the problem is pi 1, pi 2. Other problem by mu1, mu2, like that. The problems can be different. Okay? Next one, please. Yeah, I want to spend some time on this slide. So this problem is very dear to my heart because I was directly involved with this meta-analysis project. So what is happening here? Very unfortunate, and my heart goes out to all the mothers or would-be mothers in the audience. My pranam to you. My pranam to all the mothers, because we are all born out of mothers. Something very tragic is happening here. Pregnant women, they develop lung cancer, very unfortunately. They are developing, of course, we all do in the course of our life. Unfortunately, some of us, we develop the lung cancer. But here we are talking about pregnant women who develop lung cancer, two types. One, on their own, due to whatever health reasons, and the other group is they are exposed to secondhand smoking and they develop the lung cancer. How unfortunate that can be. So you don't, as pregnant mothers, you don't smoke yourselves, But somehow you're surrounded by smokers. So you are exposed to secondhand smoking, maybe at home or at a workplace, or you go to the shopping center, whatever, Maybe you meet some relatives, they smoke and so on, So you're exposed to secondhand smoking, maybe not once or twice, maybe, continuously for a while. And in the process, you develop lung cancer, pregnant women developing lung cancer, So that is very sad. So the experiment here was, each study is comparing two groups of pregnant women. One group developing, so we have the placebo group and the control group, placebo group and the experimental group, developing lung cancer. One group of pregnant women, they're pregnant and they are not exposed to secondhand smoking, but eventually some of them develop the lung cancer. And the other group, the pregnant women, they are exposed to secondhand smoking. It's not your choice, but it so happens that you are exposed to secondhand smoking and you develop lung cancer in the process. So there are two groups here. So the study is whether the secondhand smoking is bad or not, whether it should be banned. That is the idea. What is going on in each study? We are computing, naturally, pi 1 and pi 2, percentage of women developing the lung cancer, one group and the other group. And in meta-analysis, the parameter of interest is called effect size. So the effect size is the primary parameter of interest. That's just the generic name, effect size. So in this context, we are computing effect size, which is the risk ratio or the relative risk, pi 1 divided by pi 2. That's all we are doing. We are computing, we have pi 1, pi 2. The parameter is pi 1 divided by pi 2. We have an estimate of pi 1 and x1 over n1. That will p1 is an estimate of pi 1. Likewise, x2 over n2 from the other group. You have p2, p1, p2. So you can estimate the risk ratio pi 1 divided by pi 2. And there's a standard formula to construct the confidence interval for pi 1 divided by pi. So the central parameter of interest here, which is called the effect size, pi 1 divided by pi 2. Relative risk of the risk ratio, RR. So we have a point estimate and a confidence interval based on all these studies. There are 19 studies. Think about it. A lot of studies. And what is the study reporting? Like the point estimate of pi 1 over pi 2 is 1.52, and this is the CI. Anytime the point estimate is more than 1, it's a bad sign. So look at that, how many we have, two, all these two. And of course, we have study number 3, study number 4, 0.81, 0.75, study number 11, 0.79, So, sometimes we have less than 1. Maybe these studies are sponsored by tobacco industries, quite possible. You never know. So some of these studies are, short. Most of them are, saying that yes, it's bad. These 19 studies, what is the origin of the studies? Temporal spatial, all over the globe. It's it's a global problem. All over the globe and over different time points in the 60s and the 70s, 80s, all sorts of time points, different studies. And, these studies, naturally, not very cheap also to conduct, So a lot of, money involved and planning involved, all the nice designs are involved here, You want to design the study, So anyways, that's what is done, and you have results from 19 studies. It happened around 1995, 1996. We have one agency in the US called the US EPA, Environmental Protection Agency, US EPA. And they take care of the environment. Air pollution, water pollution, and land pollution, all sorts of pollution. And this is the part of air pollution, secondhand smoking, like all the chemical industries and all that. Same idea. So anyway, the chief statistician at US EPA, Dr. Barry Nussbaum. So our location, I'm at UMBC. We are about 30 miles from Washington, D.C. And Washington, D.C., that's the federal government. So many agencies are there, including the US EPA building is there. And that's where Dr. Barry Nussbaum is. And I'm only about 30 miles away from him. We are very, very good friends. I've known Dr. Nussbaum for the last 35 years. As soon as I joined UMBC in 1985, I came to know him. And by now, we are very close. So in the late 90s, Barry called me one day. He knew that I have interest in meta-analysis, and I do work on meta-analysis. He called me one day that this is the problem we have, and would you be interested in doing it? I said, of course, So I immediately got involved. So I was given the results of this 19 studies, and I was told what the problem is. And when I looked at the problem and the very statement of the problem, we are talking about pregnant women being exposed to secondhand smoking, developing lung cancer. I immediately, I feel so naturally, I was so shaken, and I terribly, naturally feel very bad. And so did I, and I thought that yes, I must help Mary out, So this long time back, when I worked at the University of Pittsburgh with C.R. Rao, Dr. Rao, Dr. Rao as Rao, Kramer inequality Rao, black hole theorem, all these various theory and all that, basic fundamental theory. He developed when he was very young, at a very young age, as a very young statistician. Anyway, but very few people know about Dr. Rao's passion for data. His doctoral dissertation was based on anthropometric data and a standard Fisher, in that station, experimental station, looking at some old skulls, looking at some ancient skulls and studying their figures and numbers and all the multivariate in nature and the discriminant analysis and Moldov's distance, things like that. Very, very applied work, That's what Dr. Rao did in his doctoral dissertation in the late 40s, early 50s. So Dr. Rao always had a knack for data analysis. So when I worked with Dr. Rao as a colleague at the University of Pittsburgh, he told me that yes, Bimal, whenever you have a data analysis problem, we all know how to do the analysis. We immediately jump into the analysis. And these days, of course, you can use R and Python or whatever, But Dr. Rao gave us nice advice that look at the data first and do spend some time on the data set. So that was in the mid-80s, I got nice advice from Dr. Rao. 10 years later, so that was in the 1990s, when I was ready to look at this problem, what I told Barry that I'll take about 3 months before I do any analysis. I was surprised. He said, why? We have everything ready, everything ready, summarized, reported in the form of a table. Why do you need 3 months? Well, I need 3 months because the first book on statistical meta-analysis by Ingram Olkin from Stanford University and Larry Hedges from the UIC, University of Illinois, Chicago. A long time back, it used to be called University of Illinois, Chicago Circle. That's what I knew in the 60s and 70s, UICC. Now they changed the name. It's only University of Illinois, Chicago. So there's one faculty there, Larry Hedges. So the first book on meta-analysis, Olkin and Hedges. And of course, in Ingram Olkin, and I knew him fairly closely for many years. So Dr. Olkin told me that in meta-analysis, there's a fundamental design problem also. That whatever is given to you, like I have 19 studies to carry out the meta-analysis. Don't think that all the studies they do qualify to be included in meta-analysis. No, we have the inclusion-exclusion principle. Whatever is given to you, some of them can be garbage, or it can be bad. They're well designed, not well, very bad planning and all that. Maybe the formula they are doing is incorrect. They're comparing two groups. Maybe the selection of the group, there's a biased selection of the groups and so on. So we must spend a lot of time looking at these studies. What I did, I read all these 19 studies. Let's talk about study 1. Study 1 happens to be a journal article about 30-page long journal article summarized in 2 numbers here. RR 1.52 and 9% CI. But actually this study 1 is a long journal article. So I read that article. what is going on. And in the article, there's a title of the paper, then there's the introduction, abstract introduction, then section 2, section 3, what are the methods, how they are selecting the two groups of pregnant women, and what is going on, how long did they follow up, all sorts of information. So I have to read that paper to finally to see, yes, there is a stat part also. We have to see whether they are applying the correct formula for the computation of the risk ratio and also for computing this CI, the confidence interval for the risk ratio. So make sure that everything makes sense. Then we said, yes, study 1 is accepted to be a part of statistical meta-analysis. Then I read paper 2, or study 2. So each of these 19 studies, they are all long journal articles in various journals, various statistical journals or applied journals. So it's not that you have to make sure that, yes, all of them, they satisfy what are called the inclusion-exclusion criteria. Then you can, of course, conduct the meta-analysis. And it was clear that, yes, we have overwhelming evidence against second-hand smoking. And since then, during the last 20 years, second-hand smoking, especially in the US, maybe in most countries, it is banned. You cannot smoke publicly in any place here. Our entire UMBC campus, beyond non-smoking zone, all the federal buildings, all the public buildings, and I'm glad that all the airlines now, I feel sorry for the smokers, but all the airlines are non-smoking and all that. So it was a very, very big study of statistical meta-analysis, second-hand smoking. Second-hand smoking is banned now. But unfortunately, we still have pregnant women developing. It's banned, but there are always it can still happen. That is at least by law it is banned. That was nice product of out of this statistical meta-analysis. Okay. So the problem here is how do you combine the results of 19 independent studies? All of them are addressing the same problem. And there's a common parameter here. The parameter is what is the relative risk. That's the parameter. And we have point estimates and CI from all these differences. If I combine, how to combine? That's the meta-analysis part. And if I combine, what we get. Okay? That is the... So I think I have given you enough examples of statistical. There's a need to do statistical meta-analysis. Okay. So let me move on to the second part. I'll skip example 7, more or less the same idea. Yeah. So let's skip this part here. Inference about a common mean of independent normals. So let's stay here. Okay. So we are talking about, remember example 1, the Paul Meyer data. You have results of 4 experiments. If you look at the sample means, suggesting that there is a common mean in the population because the sample means are very close. And sample size is small, we can assume normal. If not, then we can do some data transformation. And although the theory here is mostly based on normal, but there have been some works also based on other populations like exponential or gamma like that. But a lot of work has been done on this problem. Inference about a common mean of independent normals. So the idea is we have independent normals, there's a common mean, and the population variances, they are unknown and unequal. So this problem, kind of deceivingly very simple, easy problem, but it drew the attention of so many statisticians over the last probably 75, 80 years. There are 10 doctoral dissertations on this problem and hundreds of papers on this problem. Can you think about that? Very, very strange, At Stanford University, there is a doctoral dissertation at the University of, I think at Cornell, there is one at the University of Montreal, at ISI Delhi campus, C.G. Bhattacharya wrote his dissertation on this problem. I produced 3 PhD students. They wrote their doctoral dissertations on this problem. Of course, this is the univariate. You can generalize it to multivariate common mean. That's another dimension. So very, very strange that this particular simple topic can draw the attention of so many people. And there are papers that appeared in Analyst of Statistics, JASA, JRSSB, Biometrica, like that, in many other journals also. Why is this problem so difficult? What's going on? Okay, next slide, please. Yeah. So once we develop some theory, I'm going to describe some ideas of data analysis here, essentially meta-analysis. So the idea will be how to draw inference about the common unknown mean in the population based on samples of this type, based on the sample means and the sample variances when the population variances are unknown and unequal. Okay? So after I describe some methods, then my very last slide will come back to the data, this particular data set, example 1 and example 2, and I'll report the analysis. Okay, next one, please. Yeah, so I'll come back to example 1 and example 2. Okay, I'll report the data analysis part, the final results. Okay, next one, please. Let's keep it. Next one. Yeah. Here is the setup. We have k-independent normal population. There's a common mean mu, and the variances are sigma square 1, sigma square 2, sigma square k. That's our setup. The title is Common Mean Problem based on samples from independent normal populations with unknown variances. And of course, we have a sample size ni from the ith population. We compute the sample, summarize sample mean, sample variance, sufficient statistics, then standard exercise in BS first year honors students, sample mean normal, sample variance scaled chi-square, and they're independent. And if we have this data set, we can apply the Neben-Fisher factorization theorem. And we see that, yes, we have sufficient statistics right here. Sufficient statistics will be the pair, sample mean, sample variance, over all the k populations. So we have 2k dimensional sufficient statistics. We have k pairs, so 2k dimensional sufficient statistics. On the other hand, the number of unknown parameters, mu, sigma square 1, sigma square k. So we have k plus 1 unknown parameters and 2k sufficient statistics. And there's a notion of minimal sufficiency in the sense that this dimension, data already summarized in sample mean and sample variance, it has been summarized, the abridged form of the data, summary form of the data. It cannot summarize any further. That's a minimal sufficient. Sufficient statistics, you cannot squeeze it any further. That's it. It stays dimension 2k. On the other hand, my unknown parameter dimension is k plus 1. So we have more, that's the problem. We have more sufficient statistics than the number of unknown parameters. And that is always a source of big problem in statistics. Most of the time, whatever, you have binomial pi, p. Quotient parameter lambda, you have x bar. Normal mu sigma square, you have x bar s square. Most of the time, you have gamma, scale and shape, you have two-dimensional sufficient statistics. So most of the time equal, number of unknown parameters k, number of sufficient statistics k. There are rare examples where something like this happens. We have more sufficient statistics than the number of unknown parameters. And when this happens, naturally, there's a notion of completeness. The completeness fails, making the problem very, very hard. Problem of what? Problem of inference about the unknown mean mu. Very, very hard. Why is it hard? Because now you can see right away that there are so many unbiased estimates of mu. Each sample mean is an unbiased estimate, and because of the fact that they have a common mean, you can take any contrast. Contrast will be summation ai yi bar with summation ai is equal to 0. That's called the contrast. Like y bar 1 minus y bar 2 is a contrast. What is the expected value? 0. y bar 1 plus y bar 2 minus twice y bar 3. That's a contrast. What is the expected value? 0. Mu minus 2 mu. So you can see right away, because of the fact that the sample means they have a common mean mu, there are many unbiased estimates of 0. We call them the zero function or the error function in statistics. Many unbiased estimates of 0. Summation AI yi bar, expected value will be mu times summation AI. So whenever summation AI is 0, it will have 0 mean. So you have so many unbiased estimates of 0. And that means if you give me any unbiased estimate, I can always add that is 0 functions, keeping it unbiased. So you can see I can generate an infinite class of unbiased estimate mu. That is what is happening in this problem. And also because of the lack of completeness. So there are infinitely many unbiased estimates of mu. Which one do I select? And that's how do we compare? How do you compare all these huge class of unbiased estimates? So how do you compute the variance, then the distribution? All sorts of problems are there. That's why there are so many papers and so many doctoral dissertations. Okay. When I was an undergrad, I did my undergrad at Astos College. Back then, that was in 1962. We had statistics honors, of course, in Presidency University or Presidency College back then Astos College and Narendipur Ramakrishna Mission. So these are the 3 colleges offering stat honors. And I was a student, and my twin brother Bikas Sinha, we are students at Astos College. Very surprisingly, the head of the Dr. Shailesh Bhushan Chaudhary, late Dr. Chaudhary, he taught us this common mean problem. Can you believe that? That was in 1963, during our second year BS. In one of the inference classes, Dr. Chaudhary exposed us to this common mean problem. Now when I think back, when I look back, very, very surprising that he mentioned to us about this common mean problem. Next slide, please. Yeah, he did that, except assume that he told us, assume that the variances are known. Assume that you know all the variances. The same scenario, common mean mu, but the variances are known, then what can you do? It was one of the, I think it was one problem maybe in one of the exams, Of course, when the variances are known, there's only unknown parameter mu. So very easy now. You can show that this is the minimum variance unbiased. So this is the MLE. Under normality, this is the maximum lateral root of mu, is the UMB, and everything is very, very easy. That's not a problem now. So it was an undergraduate problem. When the variances are known, what can you do about mu? Oh, this is my estimate of mu hat. The variance of mu hat, very easy. And then mu hat being linear in normal variables, so mu hat is normal with mean mu, this variance, the whole inference problem is solved. So that was done during our undergraduate studies. Then in 1965, when he went to Calcutta University Stat Department, that's Balgan Circular Road, to do our Masters in Stat. There also our the inference Professor Horikinkar Nandi, our dissertation advisor, Professor Horikinkar Nandi produced so many brilliant PhD students, P.K. Sen, S.K. Chatterjee, J.K. Ghosh, and many more, including myself and my twin brother. We are all students of Professor Nandi. So during our masters, Professor Nandi also mentioned about this common mean problem. And this time, when the variances are unknown, and that is the practical scenario, most of the time the variances will be unknown. So when the variances are unknown, Professor Nandi talked about this common mean problem when the variances are unknown. I want you to think about Paul Meyer, 1953. He is struggling with the problem of how to combine the results of 4 experiments. He's thinking about this problem. Do you see that? Paul Meyer, he's thinking also how to combine the results of the 4 experiments with the common mean mu, unknown variances, and the sample variances are very, very different. So 1953, Paul Meyer is thinking what we have been thinking like 30 years later, all right? Or 20 years later. Okay, all right. So what Professor Nandi taught us, next slide please. When the variances are unknown, then what you do? Excuse me, can you go back please 1 second? Yeah, so this is the formula when I know the variances. If they are unknown, then obviously you replace sigma square by the sample variance. And that's what you easy fix. And that's what Professor Nandi suggested to us, that in the common mean problem, he asked us if we know about the common mean problem. Strangely enough, only the students from Astos College, we knew about the common mean problem. And Professor Nandi was very pleased that yes, and he also mentioned, you don't teach that at Presidency College or Non-Liverpool College. They had no idea about the common mean problem. Anyway, fortunately, we are taught, So Professor Nandi was very pleased. He mentioned that, so if you don't know the variances, that's what you do. Fine. That was in 1965, 66. Mentioned that easy fix is this. Then, naturally, you wanted to know, so this is a point estimate of mu. What about the properties? Naturally, a point estimate is on the starting point in inference. We want to know the mean variance and the distribution. And how do you do the full package? We want to know the inference. A point estimate is only the beginning. So what else? And Professor Nandi mentioned that it's very easy to show that it's an unbiased estimate. The EE, double expectation. You remember the formula EVVE, likewise EE. So if I take the conditional expectation given the sample variance, you have the independence, this is equal to mu. Therefore, the unconditional expectation also mu. So it's easy to show that it's an unbiased estimate with the common mean mu. That was the easy part. What about the variance of this estimate? And the distribution also. So variance of the Grable-Dill estimate there's a name for this Grable-Dill. It's not that Grable and Dill, they are the first one to suggest this. No, they did something else. I don't have time to talk about that. Anyway, this estimate was suggested by Cochrane. That was in the 1940s, long time back. That's an easy fix. If you don't know the population variances, replace them by the sample variances. Variance of the Grable-Dill estimate, EV plus VE, and this is the formula. The conditional mean is mu, so this variance is 0, and conditional variance, you can plug in the variance here, and the expectation with respect to these elements. So now I'm thinking about Paul Meyer. So Paul Meyer knew about this estimate. He was going to combine the results of the 4 experiments to get a point estimate of mu by applying, we have the sample mean, sample variance, sample size. It's very easy. And Paul Meyer was struggling. This formula is very easy. He knew right away this step, EVVE, and Dr. Paul Meyer was struggling to compute this expression. And we are struggling too. So Professor Nandi showed us this form and making a statement that is unbiased estimate of mu, and the variance is given by this. Then Professor Nandi stopped here. That was in 1966-67. We asked Professor Nandi, so what is the latest now? So do we know this? Not, of course, think about, not everybody in the class is really curious to know what's going on. But I was Bikash and I were very curious to know now. So what's the next step? And then Professor Nandi smiled at us. So, well, Bimal and Bikash, nothing is known yet. Amra ekhono kichu jani na. Ei obdi jani. There's a formula for the variance. We have no idea how to compute this. Think about it. Expected value. Of course, we have independence, chi-square. True. But look at the form. So, no idea how to compute this expected value. So that was a research problem back then in the mid-60s. Hey, how much time? I'm not looking at the time. How much do I have time or not? Suman,
Sorry. Sir, you have 30 more minutes, I think. Around 30 minutes.
Thank you. Yeah, I'm kind of taking it very easy, a kind of storytelling. That's the way I like to do it. So anyway, so now think about Paul Meyer then. Wow. So how would Paul Meyer, he cannot give up. He cannot tell his chemist friend, oh, sorry, I don't know how to do it, or I cannot solve it. Or maybe come back after 20 years, let others develop it. He could not do that. So I'll tell you what he did. But right now we are struggling to compute this variance, the expected value of this quantity. All right. So next slide, please. Khatri and Shah. Khatri from Gujarat University. Now he was the head of the department, C.G. Khatri, multivariate analysis master, and Kirti Shah from the University of Waterloo. So thanks to the Indians, the first one to solve the problem, it appeared in Communications and Statistics 1974. So right now, after all these years, back in 1974, we have the solution for the first time, the variance of the estimate. And a few years later, by Dr. Nair, Analyst of Statistics 1980, we have the distribution of that estimate. So we have to wait for a long time to get these results. I have known Professor Khatri and Professor Shah I know them very well. I have known them for many years. Professor Khatri is no more. And for me, any Indian statistician senior to me is my big brother. So whenever I see them, I give them a big hug. Dada, how are you doing? So I tell Dada, I read your paper, but. And yes, if you want, I know what you are going to say. And you understand, but yes, Dada, but. The paper is very nice, but very, very hard, very complicated. I should not say hard, very complicated expression. It's not usable. And he admitted right away. You're right. But somebody had to solve it, so he solved it. We know that this is not user friendly. Yeah, let me put it this way. It's not very user friendly, but naturally, it is an infinite series, as you can expect. Infinite series and very, very complicated. And so is the distribution. Yes, it has been solved, but extremely complicated distribution. And this is what Paul Meyer did in 1953. You can use simple asymptotics. That's what he did. And he had this formula of the variance of the estimate, infinite series. And for all practical purposes, the first term is good enough. And if we want to be a little bit more accurate, then we can include the second term on the CIs. They're all well defined. Naturally, the variance depends on the unknown population variances. And we can have an estimate of the variance by replacing sigma square I by the sample variance. All this, then we have an estimate of the variance up to the second order. That's what Paul Meyer did. Now we have an estimate, an estimated variance. We can do the inference. I'll be right back. 1 second, please. Okay. Can you hear me? Hello?
Yeah, we can hear you, sir.
Yes, sir.
Okay. But can you see me? Not really.
Yeah.
Oh, you can see me? Okay. All right.
No, sir.
Yes. I think something is going on. I don't see myself.
So do we, sir.
Shall I go out and come back or what? Anyway, you can hear me, right?
Yes, sir.
Okay. Join a meeting. Okay. I don't know how many times I'm joining. Probably it's bad. Okay, Shumon, can you hear me?
Yeah, sir.
Okay, all right. Okay, good, all right. So that's what Paul Meyer did in 1953. He solved the problem and his friends were very happy. Okay, now next slide, please. Next slide, please. Yeah. So I was a faculty at the University of Pittsburgh. This problem, this common mean problem, it stayed with me since my college days and the university days, every once in a while I'll look at the problem and do a little bit of something. And then I also studied the admissibility, minimixity thing, but I used to work a lot in decision theory. Anyway, in the 80s, when I was a faculty at the University of Pittsburgh, so I was doing a lot of work in decision theory. And there is one result, it's called the Stein's identity for normal. Likewise, there is something called the Wishart identity for Wishart matrix. Wishart is the capital S matrix, P by P, based on the sample mean variance from multivariate normal. And for P is equal to 1, it's chi-square. There is something called the chi-square identity. So when I was looking at this Gray-Deal estimate and the variance formula, I could see the connection between, after all, this variance computation is involving, this involves independent S squares, which are chi-squares. So I could see the connection between the chi-square identity and this variance formula. So I was able to apply the chi-square identity to independently derive an unbiased estimate of the variance. And that was it appeared in the Canadian Journal of Statistics in 1985. Anyway, that's the form we have. And it is very close to what Paul Meyer did in 1950s. It's a long time back, 53 and 85. But I was happy that I could do it independently and with a completely different idea. So anyway, so right now the problem is solved. So we have the estimate of mu when the variances are unknown, and you have the estimated variances. So if we want, you can stop with the first term here, and a little bit more accurate. If we want, you can add this. So that's how the problem can be solved now. So if there's any meta-analysis problem, if you are working as a statistician later on, and if you think that yes, there is a common mean problem of this type, there's a need to combine the results from experiments, independent experiments, and there's a common mean scenario, then you can think about this formula that yes, there's a way to estimate the common mean and there's a way to draw inference about the common mean also. So you can have some kind of a test also, test for the common mean. Okay, next slide, please. Yeah, I'm going to skip a few slides now. Next one, please. Yeah, approximate confidence intervals. They're all easy now because you have an estimate of the common estimate of the variance. So everything is easy now. Next one, please. Next one. Next one. Next one. Yeah, this is a nice question. What about the maximum likelihood estimate of mu? It's an old, given that is a very old problem. The maximum likelihood estimate of mu, very recent. It's only in 2007. That too for two populations, k is equal to 2. And here is an expression for the mu at MLE. It's not explicit. You have to. It depends on sigma square. Interactive. We have to solve the simultaneously all these equations here. Because the estimate of mu at MLE depends on sigma square. Sigma square in turn depends on all these things. So you have to solve simultaneously to this. And the properties, finite sample properties of these estimates also not very clear, except that you can show that this MLE is an unbiased estimate of mu, but the variance expression, the distribution of that extremely complicated. Okay, so some work has been done in this paper in 2000. So it's in a very recent paper, given that the problem is so old, and that is for k is equal to 2 only. Okay. Next one, please. Yes, let's stay here. So when I was looking at this problem, I thought that, well, okay, so we have the approximate solution, approximate confidence interval. But this is a very simple problem. After all, univariate normal, and we have all these t tests. We have results from k experiments, and from each experiment, from each data can define t. So I have t1, t2, t1, t2, tk. Or I can square t to get the f. So why don't I, it's possible to get a confidence interval based on separately for each experiment, of course. based on the t-test or the t cutoff point. So this is the exact confidence interval. So why don't I somehow combine the t's or the f's? So that is the idea now. Instead of using the approximate confidence intervals, why not we use think about the t, these are pivots. This t, t or f, they are pivots. So why don't I combine the t's and the f's suitably to have a confidence interval and overall confidence interval for mu that will not be asymptotic nature, that will not be approximate, that will be an exact confidence interval, right? So that's the idea. So why don't we combine? And I looked at the literature. Yes, there are many papers on combination of T's and the F's. Because they are pivots, so you can combine them suitably. Still, it will be a pivot. You can derive the distribution and you can get a confidence interval for mu. So it has been done. Next one, please. I'll just give the reference quickly. Yeah, there's a paper by Cohen and Sackowitz. Both of them are from Rutgers University. Back in 1984, they looked at the pivot maximum of absolute value of T. Remember, each T is a pivot, they're independent. So I look at the maximum, and based on the distribution of capital MT, we can have a confidence interval for mu. Next one, please. Very quick reference. Okay, there are some. Next one, please. There's a paper by Fairweather, British statistician, in 1972, looking at a linear combination of T. Each T is a pivot, independent. So you can make a linear combination of T, and you can have a confidence interval. They are all exact confidence intervals right here. That's the result here. Next one, please. Jordan and Krishnamurthy, they are from the University of Lafayette, Louisiana in US. They have a paper in 1996, combination of F. Same idea. You can have a linear combination of these pivots. You can derive the distribution. You can get the cutoff point, write a cutoff point alpha, and you can invert it to get a confidence interval for mu. So that's what they did. Next one, please. Yeah, this is the Jordan Krishnamurthy confidence interval. Okay, next one, please. Yeah. When I was reading these papers, this combination of T and F, various ways of combining the T's and F's, I thought that why don't we convert this T and F to a p-value, the definition of p-value, and there are so many ways of combining the p-values. In our book on this 2008 John Wiley book on meta-analysis, we have an entire chapter on combination of p-values, where p-value combination is very important in meta-analysis. Most of the time, what happens in meta-analysis, you don't have the full picture. Each study will report only the p-value. Most of the studies reported in medical journals, like the Stat Journal of Medicine, they only report not the details, just the p-value. That's what the most doctors are interested in, a p-value and whether it is high or low, like that. So how to combine the p-values? That's a very important topic in statistics. And in our book, there are so many combination methods. The second bullet here, various combination methods, about 10 of them. So we thought that here also, why don't we define a p-value for the common mean problem, and we combine the p-values. If you combine the p-values, you come up with a confidence set or a confidence interval, and which of course you can use for testing also. So that's what we did. We combined the p-values suitably to come up with a confidence interval for mu, and that will be an exact confidence interval. Next one, please. You can look at the paper 1999 paper. Yeah. So if we look at the right here, CI9, set of all mu satisfying that's the confidence interval for mu, an exact confidence interval. Okay. Next one, please. This is the inverse normal, and this is based on Fisher's method of combining p-values. Number 10. Next one, please. Yeah, there are some comparisons also. Next one, please. Yeah, there's some exact confidence on so many of them. Next one, please. Yeah. Now I think I'm almost done. So let us look at this data set. So we have results from 4x, k is equal to 4. We have the sample sizes, sample mean, sample variance. Now that we have described the various, I'm looking at the data, data analysis, confidence interval for the common mean mu. So we are going to construct a confidence interval for the common mean mu based on meta-analysis of these 4 experiments, results of the 4 experiments. So I'm going to show you the results of the approximate studies, approximate methods, and the results of the exact methods. So in all, we have about 10 methods. And if we apply all these methods, what is the final result? Okay, next slide, please. Now, I'm very, very pleased, not with any particular, I'm very pleased with our discipline of statistics that is so powerful, and the powerful method of meta-analysis also. Think about it. We have results from 4 experiments, sample sizes are very small, and we combined efficiently. In the top part, you have the large sample methods, bottom part, you have the exact methods. So you have 10 methods here. And look at the final result, the interval estimates of mu, 95% CI. Look at the final result, how close they are. So the point estimate, roughly 61 plus minus. See how tiny the interval is. They are close agreement, which is so good for our, for our discipline. That means, which means, and the powerful methods of meta-analysis. No matter which method you apply, there are 11 of them or 12 of them, exact and approximate, whichever method, you always get almost the same result. We have so much faith in the methods we develop that we can proudly present any method to our clients. It's not that sometimes what happens, if we apply one method, you go in this direction, another method gives you other results, So nobody, we cannot even trust ourselves as statisticians, Then what do we talk about the clients then, So think about it. Yeah, it's a nice place, a happy ending for all of us, for our discipline, that we have all these various powerful methods we can apply, and we get the same, more or less almost the same result, independent of the method we apply. Okay. Next one, please. The second example. Yeah. Here the sample sizes are 8, 12, 14, and 8, very, very small sample. Look at the sample variance. They're very, very different. 86, 21, 3, and 33. But in spite of this enormous differences among the variances, if we apply the meta-analysis methods, sample sizes are small. And look at the result now. Next one, please. And this is the final slide. Yeah, look at the results. The results are so close and very accurate, very, very nice results we get. So that shows the powerful method of statistical meta-analysis. Sample sizes are small, lot of sampling variation, but a powerful method of combination will give us very nice results. Okay. I think that's it, and then I have some references part. Let's look at the next slide. I don't even remember what we have. Which is there are R and SAS programs, and some of the references are here. Yeah, and there's some of the next one, please. Some of the references are here. Palmer, yes, all these. Yeah, some of these papers are here. Okay. Thank you. Thank you so much for your attention. It's about 11:18 my time, 11:18. So we have another 10 minutes. If you want to ask me any question, please feel free to do that. Okay. Thank you.
Thank you, sir, for the very interesting talk.
Thank you.
Yeah, now I open the floor for questions. So if you have any query, maybe related to this talk or maybe in general related to anything in statistics.
Yeah, please feel free. Don't be shy. When I was a student, I was never shy. Yeah. Or you have my email address. Later on, you can send me an email if you have any question related to meta-analysis, or for that matter on any topic in stat. Okay, I'm pretty broad.
Sir, I am a student of MSc Biostatistics.
Very good. Praveen, yeah, go ahead. Yeah.
Sir, should I focus on theory or should learn statistical softwares and focus on learning softwares?
Well, I'm very happy that when I was a student in the 60s, and of course even before us, the generation ahead of me, back then, very little software availability and so on, so I'm very, very happy that we went through that rigorous math stat training. Back then, we had no choice. But now these days, yes, we have an option of doing theory, and also you can apply also either built-in programs, or you can develop your own program like R, Python, and this and that to solve the data analysis idea. You can do that. But I'll still say that you should have you're working as a statistician. Of course, you can, maybe an applied statistician, you can always use the software. But, but a solid understanding of theory is absolutely essential. So that you can defend yourself, That's the idea. Otherwise, you're applying some software, they'll ask some questions, say, what happens if your assumption doesn't hold? Then what do? Then you don't know what to say. So good understanding of theory is always is always helpful. So you should understand. They not so much master the theory, but you should understand the theory and see what is the theory that is helping us to to solve the problem. And after all, your whatever R package, Python, whatever you can think of, it's all based on some formula, right? And the formula, that's the theory part. So you should have a good understanding of the theory part. Okay. If you can master it, fine. If not, at least a good understanding of the theory part. So that's my, I know these days we do a lot of data analysis, which is very important. We could not do it during our time, like massive data sets, big data, and all that. Another interesting thing about meta-analysis, like when you are talking about big data, the huge data set is very hard to analyze, but you can do dicing and slicing. You can look at some parts and you can get some relevant information out of one part, out of another part, and then finally you can put it together. That's the another benefit of meta-analysis also.
Hello, sir.
Yes.
I am Radhakanto Das from Presidency University.
Yes, Radhakanto, yeah, go ahead.
Yes, sir. Sir, my question is not so related to the present discussion.
Okay.
It is related to Bayesian meta-analysis.
Yes, so a lot of work has been done.
Meta-analysis, but my query is on Bayesian meta-analysis. Can I ask?
Yes. Yes, so let me tell you, in our book, there is a chapter on Bayesian meta-analysis.
Yes.
Done also. Yes.
I have gone through it.
Oh, okay.
Yeah. So my question is, suppose there are several independent tests. Suppose binary trials.
Right.
So each independent trials have different success probabilities.
Right.
Okay.
Oh, finally you got the book. Yeah, okay. Go ahead.
Bayesian point of view, so is it possible to to assume some sort of joint distribution of the joint distribution as a prior distribution of P1, P2 like this?
Yeah, that's normally what you do. You assume a certain common prior, like beta prior, right? That's what we do. Because after all these PIs, so the question is how before we combine, there has to be some sort of homogeneity. Otherwise, like think about the common mean problem. There is a common mean. If the means are different, mu1, mu2, mu k, and the variances are already different, then it doesn't make sense to combine the results of the k experiment because they're all representing distinct populations, mu1, sigma 1 square, mu2, sigma. There's nothing common. There's no meta-analysis. So meta-analysis is involved only when independent studies, independent sources, number one. Number two, all of them are addressing the same. There's a common parameter, like a common regression parameter in all these studies. Or like in your case, it will be a common pi. Then only it makes sense to talk about meta-analysis. But then sometimes the pies may not be quite common. There may be some heterogeneity. Then we do the Bayesian meta-analysis. You can assume some sort of distribution of the pi. Yeah, go ahead, Radhakanto.
Yes, sir. So in this case of say normal population, several normal population arising from several trials.
Right.
In that case, there is some scope of combining the variances or combining the means, and it is also possible if the Bayesian meta-analysis is carried out. It is possible to capture the variation among the trials.
Yes, you're right. Yes, that is possible. Yes,
normal case. But
yes, it is possible. Yes.
If I consider the binomial trial for different independent trials, so the binomial proportions are different for different trials.
Right, of course, yeah. Pi 1, pi 2, pi k, right.
So in that case, can we assume some joint prior distribution for pi 1, p1, p2 like this? Is it possible?
Yeah, well, what we can do, pi 1, pi 2, pi k, they are independent binomial proportions from independent experiments, but there has to be normally what you do, there has to be a common, maybe the pi i's, they are functions of a common parameter theta. So you have to have some sort of a structure in the pi i's. Like in some Mendelian study, in some genetic study, all these pi i's, we have the multinomial distribution or the binomial setup. The pi i's can be purely non-parametric, or they can be parametric also. All these pi i's, they depend on a common parameter theta, and that's what the connection is. Okay. That's what we can do.
So that will be the hyperparameter that from which we can expect the variation among the trials.
Right. Yes.
Okay, but that's unfortunately, in my case, actually we are trying to do the analysis by assuming say, probability matching prior.
Right.
There is no hyperparameter, so that we cannot interpret the variation among trials.
I understood. Radhakant, what you can do, why don't you send me an email? Send me an email with your ideas, then I'll follow it up, okay?
Yes, sir.
Yeah, please do that, yeah.
Okay. So I can send the incomplete.
Absolutely. Yeah. You put incomplete. I'll complete it.
Yeah. Actually, this will be very helpful too.
Yeah.
Thank you, sir.
Yeah. No problem. Please do that. Okay. How about Shovik Shaha? Shoikot Bera, any question? Shubhajit Das? Anjali, any question from you? Krishna Chaitanya, nice name, Krishna Chaitanya. Lord Chaitanya Mahaprabhu, any question from you?
No, sir, thank you.
Okay.
Hello, sir.
Hello,
sir. I'm Rakesh Ranjan from Banaras Hindu University.
Hello, Rakesh. How are you?
Yeah, I'm fine.
Okay.
I have a question. I have come across a problem related to meta-analysis of hazard ratio. Okay, and that was related to cancer, and that was not actually my problem. A doctor come to me and he told me to perform meta-analysis of hazard ratio.
Very good.
Done by taking log and finding the variance on log scale.
Yeah, right.
Where can I find the theoretical background of that meta-analysis of hazard ratio? I have somehow managed it using meta package.
Yeah, but whether it is hazard ratio or not, there's a general standard formula for meta-analysis.
Yeah.
If you want to do meta-analysis, first thing you have to have a point estimate, and then you have some idea about the variation. Then you always combine the way I showed you how to combine with the reciprocal of the variance.
Yeah.
The result I gave you, that's a very general result. Yeah, go ahead.
We had hazard ratio and confidence interval of hazard ratio.
Very good. Okay. So from the confidence interval, you can get the variance.
Yeah.
Good, very good. And once you have the variance and you have the point estimate, now you can combine with the reciprocal of the variance.
Yeah.
The formula I showed you is a very general result. Okay.
Yeah.
Not necessarily for the common mean. For any common parameter, that's the formula.
Yeah. Okay.
Good. Okay. Sandipon Ghosh, Dr. Anita Mehta. Hello, Anita.
Yes,
You are
sir.
here.
Good
You are
morning,
here,
sir.
huh?
Yes, sir.
Okay, good. So I have to come up with a different title for your department, right?
Okay, sir. No problem.
Okay, all right.
Okay, if you have any other question, you may ask Professor Sinha. Actually, I have a question for you, sir.
Sure.
So I'm waiting
Sure.
whether there is any other question from others or not.
Okay.
Yeah. So let's then ask my question to you.
Sure.
So as you have mentioned that many of these studies have been performed at different locations at different point of time. So is there any way of accommodating the spatio-temporal factor?
Absolutely.
Because,
Can you go to example 7? Just run it through. Very quickly you'll have example 7. Right now we are on. Yeah, go ahead. Yeah.
Just a minute.
Yeah. That's a very good question. So let's go to example 7. Yeah, give it. Okay. So in this problem here, when you are talking about whether this particular BCG vaccination is good enough to prevent TB, 13 trials, same idea, the yes/no type. And here we also have the information about the latitude, because that's in different parts of the world where these experiments are conducted. And also at the bottom we have some other year of publication. Can you go a little bit below? We have some information here. Yeah, right here. So these are the covariate information. So we have all sorts of covariate information here. When we do the meta-analysis, we are assuming that there's a common paradigm, there's a common parameter. That's where some sort of homogeneity is there. So we carry out first, before doing any meta-analysis, we carry out a test for homogeneity, whether indeed the unknown parameter is the same or not across studies. In my example, I did not do that because if you look at the Paul-Myers data, the sample means are so close, I assumed that there's a common mean. But in some, for example, in the vaccination study here, and for that matter, in any meta-analysis study, we cannot just assume that there's a common parameter. So we have to do a test of homogeneity. Most of the time, the homogeneity test will fail. It will be rejected. So there is no common parameter. Why? As you mentioned, because of the temporal, spatial nature of the studies, like in this case, this study was done at so many different latitude, year of type of allocation, publication, they are so different. So what we do, most of the time, there will not be any common parameter. There will be some variation. So we study the source of variation through the covariates. This is called the study of heterogeneity of the population parameters through this called, we have the meta regression techniques, and then so we have to go random effects model. We have to do all those things. Okay. Yeah. So in our book, there is a chapter on random effects meta-analysis, meta regression. That's a very important topic in meta-analysis, meta regression. So we can use the covariates to explain the variability.
Okay.
Mm-hmm. How come I cannot see myself? There's a problem, right?
But we can see you, sir.
Oh, can you? Okay.
No, I think the window has somehow moved. So that's why you cannot see. So there are so many participants. So the window has somehow moved.
Oh, now I see myself. Oh, okay. Now I can see myself. Okay, all right. Okay, thank you. Thank you for your attention. It is pretty late for you now. Go and have dinner and just relax. Okay. All right.
Okay. Thank you. Thank you, sir.
Okay. Yeah.
Thank you, sir, for the talk.
Sure. Thank you. Good night. Okay.
Thank you.
Good night to all of you.
Good night.
Thank you, sir.
Thank you, sir. Okay, I'm ending the meeting now.
Okay.
Thank you, sir.
Thank you. Okay. Wish you thank you. Okay, bye bye.
Thank you, sir. Bye bye.